You can only hear us, it can't see us.
They cannot see us, that's right. Okay. They can only see what's on my computer.
It's probably a lot easier to watch these like in the afternoon than at like 11:30.
It might be.
Yeah,
All right.
lecture on the history of computer math.
Yeah.
It took me to sleep. It was 50 minutes.
Oh my gosh.
Yeah.
And none of it, like, hardly any of it was on the test.
A lot of people slept during class. All right.
I stayed awake.
Welcome to third block. Hope you enjoy this as much as second block. All right. So let's start. Let's start with number 9. Now it says do example 4 except without implicit differentiation. So I kind of mentioned it a little bit right at the beginning of class, or at the end of class, about they were going to be talking about that. And if you went through and read example 4 and saw what they did, this is kind of an alternate way you can do some of these optimization problems. Because if you look at the steps that we talked about the other day, in step 3, we say to get the equation that we're trying to optimize, get it in terms of one variable. Well, you could eliminate step 3 and replace it with do the derivative with respect to one of the variables, like x, implicitly, and use the secondary equations and do their derivatives as well. So you might be doing several derivatives. You still have to do a substitution, though, somewhere along the line, using those equations. So it seems to me that just makes it a little more difficult. So I'll show you both ways here on number 9. So the problem was that they said use the equations p equals xy and x plus y equals 10 to rewrite p as a function on one variable, then maximize p over an appropriate interval. Okay, so what they're saying is we want to find the maximum of the function p. So they've already kind of done step 1 for us. They've told us what we want to maximize, and they've already given us the equation for it, okay? But it's just not in terms of one variable. So we're going to do p equals x times y. That's what we're trying to maximize. Well, this is just like number 22a. It was an area of a rectangle, which was x times y. So this is going to look very much like what you need to do in number 22. All right, and then they give you this second condition that x plus y equals 10. Now, this problem, though, would, as we hopefully get better at these, and where you would normally see this problem, I think if you went back to example 4, the actual problem was written, it said 2 non-negative numbers sum up to 10. How large can their product be? I mean, that's really how this problem would be worded in kind of a real-world situation. You're going to take 2 non-negative numbers, which means it could be 0, right? 2 non-negative numbers that add up to 10. What's the biggest product that you could get? Okay, that's what the question is. So here would be the setup. Well, the 2 numbers have to add up to 10. We know that x has to be greater than or equal to 0, and we know y has to be greater than or equal to 0. That's what they said, 2 non-negative numbers. And this would be their product. And so we'd be saying to ourselves, what are we trying to maximize? Oh, we're trying to maximize their product. What is their product? It's x times y, so our equation is p equals x times y. Okay, so that's where those equations came from. All right. So our normal way of doing it, I guess the way I told you yesterday, would be to do what? We're really at step 2 right now. We've got this. So you would take your secondary equation here, right? This is your additional information, and we would solve it for one of the variables, and this is a very common thing to do, is to try to get a secondary equation or multiple secondary equations so that you can solve one of the variables to substitute into the other function. Okay, so we go ahead and we substitute that in, and we get p equals x times 10 minus x. I would say it would be silly to get your calculator out to mess with this one. So do something like that. And so now we're done with step 3. And what was step 4? Again, I'm not crazy about memorizing these as steps, but I think if
Those be the 2 things you remember.
Yeah.
right,
Or find critical points of the equation.
fine, thank you, find, okay, find the critical points. Now, we've got the thing we're trying to maximize, so we want to do the derivative, set it equal to 0, because that's possibly where they could be. We also want to check if p prime is ever undefined, which it never is, because it's just a linear equation, which would never be undefined. Yes, but
Do you only do the shenanigans with the square root if you're trying to find it like a point on a graph? When we did like for 4 with the x squared plus the.
I don't know what shenanigans.
This,
Oh, like trying to find distance, the distance formula.
yeah, do you only use the distance formula when you're trying to find a point on a graph?
Well, okay, here, let's back up. Step 1 is identify what we're trying to maximize or minimize. In that problem, in number 4, they wanted us to find the minimum distance from that point to that line. Okay, so I'm thinking, okay, I want the minimum distance. Step 2 is write an equation for the thing you're trying to minimize or maximize. So step 2 in that problem was write an equation for distance. So in that problem, I needed the distance formula, right? Yeah, so that's why we did a distance formula. If I need, one of the things we're going to learn next week is we're going to talk about some business examples. We're going to talk about profit. If I'm trying to maximize profit, I need to write a profit equation. Well, what is profit? Well, it's the money you bring in minus your costs, right? It's your revenue minus your costs. And so we'll have to, we'll just have to write that. So we did the distance formula there because we were trying to minimize distance. Right. So in this one, step 1 was what are we trying to maximize? Here we're trying to maximize this product. So what do we need? We need an equation for that product, which is what P equals XY was. Okay? So the equation you write depends on what it is you're trying to maximize or minimize. All right, so we do the derivative, set it equal to 0, and that comes out to be x equals 5. So that's one of our candidates. We don't have any candidates when P prime is undefined, because it never is undefined. And so the other thing we have is our endpoints. And our endpoints, what's the question you have to ask yourself when you're looking for endpoints? What's the littlest x can be, the input, and what's the biggest x can be, right? What's the littlest x, what's the biggest x? Well, the littlest x, and it's not always x as your input, and most of the time we do, we're just comfortable with that. Since we're setting up the equations, we can use whatever variables we want, so we usually use x. So what's the littlest x can be here? 0. And what's the biggest x can be? The biggest x would be 10. Because they're non-negative numbers. So you couldn't have 11, because then y would have to be a -1 for them to add up to 10. So they have to be positive or 0, and so if x is 10, then y would be 0. So that's the biggest x could be. So 0 and 10 are our 2 endpoints. So we can now do a list of candidates, because we have multiple candidates. Yesterday we said if you only have one candidate, if there aren't any endpoints, then you may need to do, say, a number line or something like that. All right, so we're going to plug those back into the original. So we're going to do P of 5, we're going to do P of 0, and we're going to do P of 10, the product when x is each of those things. And probably go back to, it doesn't really matter, this would be a pretty good version of that to plug into right there. That'd be pretty simple. So 5 would be 5 times 5. 0 would be 0 times 10. 10 would be 10 times 0. So the question was, what is the max product? And so that's the output, which is 25. Which you notice is when x and y are both the same, when x and y are both 5, which is this problem is essentially the same as 22, which was you given a rectangle, given perimeter, what's the largest area? It's a square. Okay, this is basically like perimeter, and this is, it's almost the same problem as 22. Yes. Right. Yeah, that's kind of, that fits in there. Let me do one other let me talk just briefly about what they meant by the implicit differentiation route that we could do. You don't need to write this down, okay? But instead of, as an alternate to getting it in terms of one variable, we could have said, let's just do the derivative of this the way it is, but we'll do it with respect to x. So what's the derivative of p? P prime. Or we could write dp dx, right? I mean, we could use that notation. What I like with that notation is it tells us we're doing it with respect to x, right? And what's the derivative? And of course, to do the derivative of this, we have to do what? The product rule, right? So the derivative of x is 1. Now, why wouldn't we say x prime then? Because it's with respect to x, right? X prime would be like dx over dx. It's just 1. So the derivative of x is just 1 with the y left alone, plus the derivative, or x left alone, and what's the derivative of y? Y prime, right? dy dx. Okay, the derivative of y is y prime. And so we could have done that. Then what you have to do is you have to also take your secondary equation and do its derivative. So what's the derivative of both sides of this? Well, derivative of x is 1, derivative of y, y prime, and derivative of 10, 0. And then we subtract a 1, and we get y prime is -1. And then that we substitute back into there. So now we get p prime equals y plus negative x. Now, the problem we got there is we still have the y in it. So what do you end up having to do? You end up having to solve the top one anyway. Now, it doesn't always happen that way, but in this one you do. And so you still end up putting in y equals 10 minus x. And so we get 10 minus x, which is 10 minus 2x, which I believe, if we look on the other page, isn't that the same thing we had for p prime? Okay, so it does work. I mean, but it seems like an unnecessary step to do. And probably the only time that it might be good to know that's an option is if this one is really hard to solve and the substitution is really ugly and messy, and maybe doing the derivative that way would make something easy. But none of the problems we do with that, I think it's just as well to do what we were talking about in the other. So that's what they were talking about in 9 with that implicit differentiation. All right, let's get to number 17. The world famous Shanghai problem. So, would it be safe to say that none of you will be accepted into Shanghai University? Is that what you're saying? If that's on their college entrance exam, okay?
Do this problem.
One of the things now that is uncalled for. That is not politically correct, and we should not be laughing at that. All right. Okay. Yeah, see, this is being recorded, Jared. They probably didn't hear it. It's a good thing. All right.
Let's repeat ourselves.
Oh my gosh, that's a new problem.
No. All right. Now, here's what the problem says. You've got the parabola 1 minus x squared. Okay, so it's an upside down parabola, crosses at a height of 1, the y-intercept. Also hits the x-axis at 1 and -1. Okay, and it says that the triangle that fits snugly inside of the triangle. You may even use the word snugly. Okay, it does. Okay, and so the question is, what? And so by snugly, it means those two sides of the isosceles triangle touch the curve. They're tangent. Hint, hint, hint. Tangent to the curve. They are tangent lines to the curve. Now, I like this, being able to look at this, because we can move the idea is that, see, that triangle gets bigger and bigger, and then it gets smaller, 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 but then as you go here, now it's getting bigger and bigger and bigger. Okay, so if you watch this number, now this isn't the actual number because it's based on the units here. So that's not the actual answer. But if we move it, you can see it's getting bigger and bigger. So somewhere right in there, is where it kind of seems to be the smallest. So it makes sense that there would be some spot for that point where this would make the triangle be a minimum area. Okay, so that's what we're trying to do. The problem, the difficulty with this one is getting it set up, right? Now, so let's draw ourselves a picture of this. And we've got the parabola here. And I really, since it's symmetrical, I really only need kind of one side of this. I mean, the other side would just be a mirror image over here. Okay, but there's my triangle. And this would be the point x and 1 minus x squared. Remember how we did that yesterday? I mean, we could call it xy, but we know this equation of the parabola is y equals 1 minus x squared. Okay? And then this would be just something 0. And this point up here would be 0 and then something. Now that would change. We saw that in the picture over there. As I slide this point right here along the parabola, this point down here changes and this point up here changes. So these, where the blanks are here, those are going to be variables, right? There's going to be some letter, some variable there that's going to change as this point changes, okay? So we need to find them, because this is our height, right, of our triangle, this y value, and this x coordinate is not our base, but it's, what would this x coordinate of this point be? That'd be half the base, which actually, in a triangle, is what we want, right? We want the area of that triangle is half the base times, half the base times the height, right? So this number right here, whatever it is half the base, and this number up here is the height. So this is what I'm trying to minimize right here. So there's step 1 and 2. I've identified what I'm trying to minimize, which is the area of that triangle, and I've written an equation for the area of that triangle. Problem is, it has 2 different variables in it. Now in this case, it turns out we're not going to want to get rid of one of those variables. We're actually going to get rid of both of those variables and replace them with a new variable, another variable. All right? And the thing that's changing throughout the problem is this point, the location of this point. You might notice in the other picture I called it A. Okay? Why not just call it X? Well, here's why I wanted to call it A. Because what I need to do to find this point and this point is write the equation of this line. Think about that a minute. If I had the equation of that tangent line, now it's not going to be an exact equation, right, with just numbers in it, because that we don't know what that line looks like, right? What slope it is, because we know that this moves, right, and that line changes. So its slope and its y-axis, those will be variable, right? Those will be changing. So there'll be some letter in there. All right? But here's what the equation of a tangent line looks like. If I could write the equation of that tangent line, right, then I would be able to find these 2 points here. Think about it. If I had the equation of this line, right here, I could put a 0 in for x. I could put a 0 in for x, and whatever the rest of that came out to, that would be the y. That'd be that. And likewise, I could put a 0 in for this y, and solve for x, and whatever x equaled, that would be that, and that'd be that half base thing. So that is the trick. I mean, there's a lot of tricks to this one. Now, this is the first time we've seen it. As we go through the year, I will many times reference, well, there's another problem that's similar to this. I may reference that one as well. I may reference both of them. I'll talk about, hey, this is like the Shanghai problem. You know, and hopefully, as we get towards the end of the year, you'll read a problem, you'll see a problem, and you'll go, hey, this is like the Shanghai problem. This is the strategy I need here is like what we did in the Shanghai problem. Right? So it will get hopefully easier, or something you will be able to do. First try it, this one is really difficult. All right? All right, so anyway. So since I'm using x and y in my line, now see, I'm using x and y here for the parabola equation, and now I want to use x and y for the line equation. They're 2 different equations, 2 different sets of x and y. So I better not mix up those x's. So that's why in my picture over there, I called this point A, and 1 minus a squared. Okay, I would rather call that point. So what do we need to write the equation of line? Slope and point. Well, we know one point, that red point, is on the line, right? So I'm going to put the a in there for my x, and I'm going to put the 1 minus a squared over here for my y. So that's the point that's on that line. Now what's the slope of the line? How do I determine the slope of that tangent line? No, well, that would be one way. If I had 2 points, if I knew 2 points on that line, I could, but I don't, right? I know this red one, I don't know this one, I don't know the whole point, and I don't know this one. So, but that would be an option, and actually we're gonna do a problem later, a month or so, or whatever, I don't know, we'll do another problem where that would be a good strategy. So what's another way to get slope of one? The derivative, because it does, isn't that the definition of derivative, basically, is the slope of the tangent line? So what's the derivative of this parabola? So y prime is negative 2x. So what would be the slope at point A? Negative 2a. The slope at point A would be negative 2a, and that's really, well, there's a lot of keys to this problem, thinking about, any of these. There's a lot of places you can start, but right there, the derivative of the parabola and also the derivative of that line, the slope of that line, would be negative 2x, so at point A, it would be negative 2x. All right, so we just put that in there. Now let's go ahead and let's distribute that out a little bit. Actually, it's probably not even smart to distribute that out. It's probably best to leave it like that. So now let's do this, let's do the top point, that's easy. So let's put a 0 in, so this is, we have the equation line right here. So now let's put a 0 in for x. So what do we get? We get y equals negative 2a times negative a plus 1 minus a squared. So y would equal 2a squared plus 1 minus a squared. So y would equal a squared plus 1. Now what do we say that is then? What's that y? This is AP count.
recording.
Yeah,
We're recording.
I walked in. They're doing a learning curve on AP courses at the high school.
This is the best one.
They're great.
And we're already recording, so.
And I'm
You're already
recording
I'm
this for
sorry.
my third block class too. Audio.
Sorry, third one.
Sorry, third block, you don't want to be on TV. All right. So anyway, back to the world famous Shanghai problem. All right. So what did we say y equals a squared plus 1 was? Would be the y coordinate of this, which is also what part of the triangle?
Height.
The height of the triangle, right? So that's going to be this h right here. Okay? Now what? I got to find this point. Well, what do we know about this point? The y is 0. So we're going to take this same equation and we're going to put a 0 in place of the y. So now we have negative 2a parentheses x minus a plus 1 minus a squared. Okay, what do we want to do with that? Solve for x, right? So what do you want to do? So, I don't think we should distribute, I'll be honest. I think it would be better to move this over first and then divide by the negative 2a. Okay, so let's do that. So let's subtract that over, which would be there. I mean, yes, I could have distributed. You might be right. That might have been smarter. Okay, we got that. Then we could divide by negative 2a. Right? And then what? Add a over. Yeah, I might have been smarter. Now we're going to have to get a common number. All right. So what would that be? So x here would equal, get a common denominator, I'd make negative 2a, negative 2a. So this would be negative 2a squared plus negative 1 plus a squared all over negative 2a. So what is that? negative a squared minus 1 on top, negative 2a on the bottom. Can we take out a negative? Would that make that nicer and cancel? So in the end, we're going to end up with a squared plus 1 over 2a. And that x is what? What is that x right there then? Half the base of the triangle. All right, so when that's all said and done, we're going to have to go to a new page, but the area of our triangle is a squared plus 1 over 2a times a squared plus 1. And what step are we on?
We're ready for
Step 3, right? I mean, we just finished step 3. Yeah, we're ready for 4. We've now got what we're trying to maximize, or in this case, minimize. We're trying to minimize that, and now we've got it in terms of one variable. Okay? So, next page. A prime, go ahead and get your calculators out, and we'll get somebody.
Oh, I'm not even logged in.
Gotta be logged in. We'll pick Tiff.
You said no, we wanna put A on the bottom.
All right, Tiffany. Tiffany is our presenter. All right, here we go. We're going to do the derivative of that function. What was it? A squared plus 1 all squared. Or x squared plus 1 all squared. Essentially, weren't there 2 of those on top? 2x squared plus 1's on top, so you can square that top. All right, derivative of that. Okay. So, Jake, did you end up getting the same answer? Remember you said you get the same x value on 11 as you had on 17? Well, but I think we are going to get the same, aren't we? Because didn't 11 also have 3x squared minus 1 equals 0? Because that's what's going to happen. Well, I know. But did you do it algebraically, or were you?
I used a half pH and essentially XY. Maybe erase this.
Yeah, darn it. I just, but I didn't remember what the actual answer was. But anyway, we want to do the derivative of this, or excuse me, we want to set this equal to 0.
I put 1 minus x squared equals y on that. And then do the derivative of that, set it to 0.
Well, you're the only one. All right, so well, right. I mean, like you said, getting it set up. Yeah, that was a great one for TV, wasn't it?
I'm sure they were like not taking this.
We should have said something like, we should have had you say, oh, this, can we do a harder one, please? Yes, please, let's do a harder one. This is really
Yeah, we should have said that joke again.
okay, oh, yeah. Okay, go ahead and hit enter, okay? So, and go ahead and hit Control Enter so we get the decimal. Now, okay, I'll have to look at that, Jake, and see. Somebody else got that and said they did. Let's hold off for a minute. Let's hold off for a minute. But back to our work. So we got that derivative, right? We set it equal to 0. And so we got x equals, what was it, 0.577? Root 3 over 3, right? It's root 3 over 3. What's that? Yeah, it was the same number as 11 because it ended up being that same equation. So that's what Jake was asking about earlier. And it was plus or minus, but we don't want the negative one. I mean, that would just be the other side of the triangle, right? The negative 0.577. So we have that as our possibility, which we feel pretty good about. But we also had a prime undefined, okay, which was when x was 0. Of course, again, when you get into these problems, it's possible that you just don't do a straight list of candidates. If you want to, in paragraph form or sentence form, discuss, okay, x can't be 0 because if x is 0, there'd be no triangle. It'd be up there at that peak. It'd just be a horizontal line, right? I mean, there'd be no triangle. If I move that point A on that other picture I had all the way up to the top, it'd just be horizontal. It'd never come down and touch the x-axis. So that would be an infinite area, that kind of thing, okay? Because we wouldn't even be able to put a 0 into our original A function, right? If we tried to plug 0 in, we're going to get undefined. Well, why is it? Well, this is why we talked about all this stuff about limits, because in your list of candidates, you could do this. So what would be our endpoints? Let's talk about endpoints. What's the littlest x could be? Well, yeah, you might say 0, but technically, if we just got in saying it can't really be right. Now, what's the biggest x could be? Go back to your picture here. What's the biggest? Now, remember, our x, by x, we mean this a value here, right? That's our x. That's our input here. What's the biggest a could be? It's going to be 1, right? The biggest would be, if it's right here, is 1. So we do actually have another candidate here. We have a legitimate candidate. I would say 0's really not, but we could do it, and I'll show you what we'll do with that.
How would I have known that without your little picture?
Well, you'd have had to do this picture. Okay, this parabola, you would need to know that 1 minus x squared crosses here at 1, crosses here at negative 1, because you would graph that yourself. I think it did also say that a little bit there. So we know that this point, when I drag it, could be as big as 1 and could be up here. All right, so we go on here. So this is a legitimate endpoint, a of 1, because that will really give us a triangle. And then we have 0.577. And we plug that into our original a, which was little a squared plus 1 all squared all over 2a. So we plug in 0. Now, I would not want you to put undefined or does not exist. Essentially, what you should say here is approaches infinity, because that's what's happening. As you put a 0 in for a, you would get 1 over 0. Well, we talked about that. That basically means like infinity. So as a gets really close to 0, what's happening is that's like a horizontal line, and the area is getting bigger and bigger and bigger and be basically infinite. Well, that's clearly not a minimum. Okay, so that's what we talk about, discuss in behavior. Do list of candidates, discuss in behavior. Okay, you put in a 1 there, you get what? 4 over 2 would be 2. And then you put this number in, and what do you get there? Anybody have that up yet? What do we get when we put that 0.577 in? And let's go 577. Go ahead and grab it again, Tiffany, and put 5773502 or something, just so we get a few more. It probably won't matter, but I'm always nervous about that because some problems. No, you're fine. Yeah, put root 3 over 2, and then hit control, or root 3 over 3, and hit control enter so we get a decimal. So 1.155, and did that matter? Arrow up, did that make a difference in the third decimal place by doing that? Not really, but it did make it made a difference in the fourth decimal place, but not in the third. So you do want to be careful. Okay, so 1.155, which is our minimum area. Okay, so Dylan, back to your comment about, I don't even know what's going on here. Well, here's the lesson of this. Here's the lesson I want you to take of the Shanghai problem, because you will see many different problems with a tangent to a curve, but you don't know specifically what point it's tangent to. It could be variable. And so instead of knowing an actual point, like at 2, find the tangent at 2, what we're doing is find the equation of the tangent line at A. So what we get, we still do the same thing. To write the equation of the tangent line, you want a point and a slope. Well, in this case, the point is A and 1 minus A squared. You should know that, because if you know what the curve is, you plug an A into it, or whatever your variable name you want to be, you'll know both of those. You get what I'm saying? So you'll have a point, so there's your x and your y point. And how do you get the slope? How do we get the slope? The derivative, right? If you have a curve, you can do the derivative, and you can put your a in there. So the only difference here from what we've done on tangent line equations is instead of having a number where it was tangent, we had a variable where it was tangent. But we still did the same stuff. We have a slope and the point, okay? Then, of course, the other part that made this hard is, okay, now I've got this equation of this tangent line with these a's in it, and now I want to know the x and y intercept of that tangent line. So we simply put a 0 in for x, we put a 0 in for y, and we solve for each of those. And so we were able to get these points in terms of a. Okay? I mean, so that's what happened. Now, how would you have thought of doing that? You haven't done one like that before, so you're not doing it. But now you have. Okay? Now you have. And so now we've talked about that. Okay, you've got a tangent line at a variable point you don't know, so you use a variable instead of a number, and you go through that. Okay, now let's talk about what, Jake, what you did. Fill me in with this again. You had y equals 1 minus x squared. Okay, we have a triangle that's area is 1/2 base times height. And let's see if this was kind of a fluke thing.
Well, on that other page, how come you like with 1/2?
Because this is the base of my triangle, all the way to there. But this x coordinate is only from here to here. So this x coordinate right here is half the base of that triangle. So in the area formula, half the base is this x, is that right there. You see, here's my triangle right here. Okay? Here's the base of that triangle. This line right here is half the base. And that is the x coordinate of that point right there. Okay, so that's half the base. And this right here, this y coordinate of that point is the height. So that times that is the area of the triangle. Okay, that's why. So I really didn't ignore it. I did use it. Okay, Jake, tell me what you were doing with Derek. Did you say you had done something with this? Jake, go ahead.
Use x and y instead of b and h, I guess.
Okay.
And then substitute in for y, the 1 minus x squared.
So if that equals 0 times everything by 2, you'd have 1 minus 3x squared equals 0, and that would come out plus or minus root 2 over 3.
And you told me to do it wrong.
Well, you did. Yeah,
I like that way.
yeah, that's nice, especially when it comes out right. Here, what you did there, here's, and I'm going to have to look at that more to see why that came out right. I don't know if I've ever had anybody try that, or maybe I just ignored it. But here's the problem. X and y, in this equation right here, x and y are points on this parabola. This point and this point and all the points here are not on the parabola. So you used as the height of your triangle, you used y as the height of your triangle. But y is points, but you substituted this, which is points on this parabola. So that would be saying that your height of your triangle has to be a point on the parabola, and it's not a point on the parabola. And so that's why I'm really curious why that. I don't know if that's just pure luck that came out to be that point.
Parabola's basic points 1, 1, negative 1, and 1. Whenever they use points like that, even simple estimations like that.
Maybe that's why it is, because of the 1. Because if that would have been 2, if the equation would have been 1 minus 2x squared or something like that, and then those points, I don't know, we can try it with different ones and see. I'm guessing it's different. Well, we won't. We're not good at it right now. But I want to kind of look at that.
That's fun in your free
That
time.
would be a fun thing to do on the bus up to Lincoln. All right. So anyway, we've got stuff we got to do. So anyway, that was 17. So that probably not going to be on the quiz. All right. So, all right. Homework for tomorrow. Let's get started, and I'm going to do a couple with you, and then you're going to have some more time. Yes.
Okay, so on that one then, where do you get the A from?
Well, here's what I did. Here's what I did is I wanted to write the equation of a tangent line. And so the stuff in black is just my basic format of a tangent line. And it goes to what I was just telling Jake. I'm going to use X and Y here as points on the line. But in the parabola, X and Y are already, in my problem, points on the parabola. So what I wanted to do, I couldn't say, okay, I couldn't come in here and say, okay, here's my point. I need a point and a slope, right? So I couldn't come in here and say, well, my point will be X and 1 minus X squared. Because if I put an X there and a 1 minus X squared, now I'm using X for two different things. I'm using X for points on the line, and I'm using X for points on the parabola. And I couldn't do that. So I had to say, so let's call this point where it touches. Let's give it another name. And so I called it that. That was one. All right, number 28. Read number 28, please. Same section, yeah. Page 241. Now we're going to do part B together, and I'll leave part A. A is easier than part B. C is very much the same as part B. And then D, you won't even have to worry about it. Okay?
On the assignment sheet, it says we have a business packet too.
Yes.
Say that.
Well, no, yeah, I will get that. I'll get that for you. Yeah. Yes. There are some problems in the book, and there's this other. Remember, I was saying earlier we'll be doing business example like profit and stuff, and so there's a packet from a different textbook because this textbook doesn't do very good or very many business examples. All right, so 28B. So you got the idea? We've got a restriction, and this is true. I mean, they do literally have restrictions on, or if you go beyond their restrictions for something you can mail, it's very expensive. Okay, if it's especially long or especially flat or especially because they're hard to pack, and they have to do extra stuff, and so they charge more. So this restriction that they talk about, the girth of the package and stuff, this is actually kind of how they do set rates and what kind of things. That's why I like the post office stuff where it has pre-made boxes, because they have them in ways that are easier to ship, easier to pack, and so forth. All right, so step one, identify what we're trying to maximize or minimize.
The size of perimeter of the mailbox.
No? Volume. Volume of a box, a three-dimensional rectangular prism, basically, right? Now, so that's what we got. Now, we probably should draw a picture here. Now, do they mention something about, in part B, do you notice they talk about two cases? Two different situations? Okay, there are two different situations you have to do here. All right, so once again, here, problem 28, looks like it's just one problem, but it's got three parts, and in two of the parts, they have their own two parts. So, imagine that. But here is case one. It says it depends on which one's the long side. So let's do a box that is tall. Okay, so let's draw that. And forgive yourself if you can't draw as good as me. That's okay. All right. Now, how do we want to label this? By the way, let's let's write, let's do step 2. We've identified volume as what we're trying to maximize, right? And so step 2 is write an equation for volume. Length times width times height. Correct? So this is what we're trying to minimize, or in this case maximize. Maximum volume. But still fit within their guidance. All right, now, what did they say? Didn't they say it has a square base? That's going to be helpful. Okay, so how do you want to label it? Yeah, I like X myself rather than L and W. I'm thinking. You know what I mean? So what should I label this one down here? X and X, and that'd be Y. Okay? Now, I'm going to go to a new page, whoops, and do case 2, which would be instead of Y being the long side, right, the square base being the long side. So that would be a box that would look like this. I did that bad. What's that? That's part A. But it might not be, I don't know if the largest one would be a cube for the given restrictions. That's possible. We're talking about one that has one side longer than the base, or the base is the long side. So if I did, let me give myself a little room here. Okay, so assume we had something like this.
We're using
Okay.
both.
Well, you have to do both. We have to do two. There's going to be 2 separate problems here in 28B. Okay, and you'll see why here in a minute. But the restriction says that the long side, is it twice the long side? What did it say? The long side plus the girth. Is that what it says? The long side plus the girth.
It
And
may
the
not
girth
exceed 100
can't exceed 108 inches. So the long side plus the girth, and the girth is a perimeter perpendicular to the long side. Perimeter of a cross section perpendicular to the long side. So it's going to make a difference depending on which one is the long side. If X, the part of the square base, is the long side, that's going to be something different than if Y is the long side. Okay? So let's go back to our first situation. So the volume on this one is going to be what? X squared times Y. So there's our step 2. Write an equation of the thing we're trying to maximize. Right? Step 3 is use secondary equations or other information to get that in terms of just one variable. Well, that's that 108 inches business. The long side plus the girth, and we'll assume it says it cannot exceed 108, so we'll assume that means that we want to use the full 108. That would maximize our volume. So we don't have to do less than or equal to. We can just say long side plus the girth is going to equal 108. We're going to use as much as we can. That should maximize the volume. So in this problem, what's the long side? Y. Plus the girth. What's the perimeter of a cross section perpendicular to the long side?
4x.
4x. Right? Because here's the long, well, I mean, we can laugh at that, but seriously, think about it. It isn't that hard. This isn't beyond what we can do if we just think of it. Okay? Perpendicular to the long side. Here's the long side. Right? One option on these problems is to give up. And I understand in the early parts they're pretty difficult, but as we go along here, come on. We gotta try it. Here's the long side, Y. Perpendicular to that would be this way. So we're talking about the perimeter perpendicular. That would just be around here. Right? That's all it would be. Which would be just around here. What is that? 4. Right? So perpendicular to the long side. So we could go, you could draw it in here if you want, But that's the girth. Okay? the perimeter perpendicular to the long side. So that's 4x. So the long side y plus the girth 4x equals 108. That's our secondary information. Okay, so there's step 3. Well, no, we're still on step 3. We need to use that now to do what? We're going to solve that for y. And we're going to substitute that in here. So we get x squared and then times y, which is 108 minus 4x. Okay, and so, and again, it's not, the math isn't too hard there. Let's go, I mean, you can get on your calculator at this point to do derivatives and stuff for you and whatever. But, so essentially we have that. Okay. And so now what? V prime, 2 parts to V prime, where it equals 0, where it's undefined. That's a nice cubic, so V prime's never undefined. Now, to be honest, the calculus doesn't really come in until step 4. But, I mean, really, the first 3 steps are kind of an algebra 2, kind of just understand the problem, choose a variable, draw a picture, set up an equation, maybe some geometry as far as knowing the equations. If we have any difficult type pictures, I'll probably, like on this one, I might have said volume of a box is width times height, just so that, I might have given you that. I mean, so it's not like I'm expecting to remember all these crazy formulas from geometry and stuff. But, okay, but the calculus part, the steps, the process, really, I think from this point on, this is just stuff we learned in chapter 2, list of candidates. Now, there are some harder parts to it, like figuring out what the endpoints are, or maybe it goes to infinity, so you have to, so it's not quite as straightforward as what we did in chapter 2, but it is those steps. Okay, it is those steps. So now we do the derivative. So you're ahead of me here. What do you got? 216x minus 12x squared. You set that equal to 0. Okay. Zero or 18. Okay. 0 or 18. Okay. And so we said V prime's never undefined. We've got those as possible candidates. And then our endpoints, what would be our endpoints? And what's the question we ask ourselves? Littlest x can be, so I would come up to this long side plus the girth equation, I think, to do that. The littlest x could be, those pretty obvious, right? 0. Okay, the biggest x could be, no? Divided by 4. So 27, right? In other words, if we used everything for x and nothing for y, but again, it wouldn't even make a box if we didn't use anything for y. Plus, y wouldn't be the long side anymore either, would it? So technically, it's probably even less than 27, to be honest with you. I mean, if we're going to make, if literally this means y has to be the long side, then y has to be at least equal to or bigger than x, right? I mean, otherwise it'd be a cube. So probably wouldn't be right to do 27. There probably should be what? Well, not 54, because would it be 54 divided by 4? Now wait a minute. Let's think about this. Yeah, let's do that, because basically we're saying if y is equal to x, right? But then we want y to be bigger. So if y is equal to x, you have x plus 4x. Yeah, 5x. So what's 108 divided by 5? 21, right? So if x was 21, if x was about 21.6, then you'd be using your 1/8 here, right? And y would be that, and x would be that, and we really couldn't go under that. So what was that, 21.6 repeating? Or no, it was even. It was exactly 0.6. So technically be that. Now, if we were doing that problem and you put 27, it'd probably be okay. But I don't think that's going to end up being one of what we want anyway. All right, so now we can do our list of candidates. And so where do we plug these? The original is V, right? We got a lot of equations going on here, so it's always important to keep track of what we want. So V of 0. V of 21.6 and V of 18. Okay, so it's pretty easy to see if x is 0, we're just going to get that. But the other ones, okay, and Tiffany's doing the curly bracket thing for us. There's a way of plugging all those in. So, what do we get here? 10,000 for 21.6. It was like 10,007 or something. That. 77. Okay, but we're looking for large volume, so it was 11,000. 11,664. So we're looking for max volume. Now, what did the question ask? Because we still have part 2 to do, so we're not ready to.
Find the dimensions of
The best one, the one that has large volume. So let's just hold off until we do part 2 here, before you decide if it's that one or not, right? But that was with x being 18. All right. So what is going to change here? The volume is still x squared times y. But now we've got the girth, right? The long side plus the girth. So long side plus the girth has to equal 108. So the long side is x plus the girth perpendicular to the long side. Here's this is the long side. We could do this one. No. Perpendicular is this way. So, no. So wouldn't it be this perimeter here? Yeah, wouldn't it be 2? It'd basically be this perimeter here, wouldn't it? Which would be 2x plus 2y. So so it's 3x plus 2y equals 108. So you can see it didn't matter which of those was the long side. Okay, when it came to the girth of the package. All right, so we need to divide that. Let's just solve for y again since we did that last time. So we subtract the 3x. We divide by 2, so that'd be negative 3 halves x plus 54. And then we substitute that back in. So x squared times negative 3 halves x plus 54. And distribute that through. And then what? Derivative. Again, it's just a cubic, so v prime is never undefined. But we always want to remind ourselves that that's one we have to look at. The derivative would be negative 9 halves x squared plus 108x. Set equal to 0. Oops, you got time sign. Yeah, you got time sign. Yes. There we go. And then we'll solve that. Okay. So we get 0 or 24. And our endpoints, we ask ourselves what's the smallest x could be, which of course we said was 0 again. And what's the biggest x could be. So we come back up maybe to this. Equation here. And we want x to be, so again, we could do the same thing again. Couldn't we? I mean, we want X to be the longest side. So X has to be more than 21.6, right? But so we could just do, so in this case, we could literally let Y go to 0, right? The biggest X could be is if we used it all for X. So that would be 108 divided by, it's actually what we're saying is X couldn't be 0 here, could it? Technically, X couldn't be 0. Good, because it wouldn't be the long side. So what would what's the smallest X could be? Yeah, that's the 21.6. Yeah, that's the 21.6. So technically here, 21.6 would be the smallest X could be. And the biggest would be 108 divided by 3, which is 36. Right. Because if X is less than 21.6, then we wouldn't, we'd be over the, it wouldn't be the longest side. So that would kind of throw out that one as a possibility. So in our list of candidates, we would have V of 21.6, which we had done earlier. But that actually it's a different volume formula now with different X, isn't it? So that would change. And no, because that'd be a cube. That'd just be a cube with it. So I'll bet that comes out the same. And then V of 36. And 24, yeah, and 24. Okay, so we're going to plug those in. 21.6, 36, and 24. And 36, of course, is 0 because we use all of it for X, so that makes sense that one's going to be 0. Oh, whoops, you put them into the derivative.
Oh.
No, got to go up one more. Maybe you don't have the original. Yeah. But it actually should be, I think 36 will come out to be 0. Yeah. It'll actually come out. Yeah. Yeah, it's this one here, -3 halves X cubed plus 54. Okay, so this one I'm pretty sure 36 can come out 0. But again, the thing we're spending the most time on, I don't know if we're spending most time on it, but the part that we really got to work on is all these different problems of setting them up. And they're just different. I mean, one's a distance formula, one's volume of a box, one's, area of this, and one was area of a triangle. I mean, there's just all kinds of possibilities. And so that's where the thinking comes in. I mean, that's where you've got to think, draw pictures, label, think about it. Once you get the equation set up that you're trying to maximize and minimize and get it in terms of one variable, then it's just follow steps. Look at the 3 points. Oh yeah. I'm not saying you don't have to think anymore, but it's now you're doing the calculus part. Now you're doing derivative equals 0, derivative undefined, endpoints, and that can have its own set of issues, no question about it. But at least they're similar issues. But okay, what did we get? There's that 10,077 again, and this time the other one was what? 10,368. So the other one was bigger. All right, so for the final answer then, they wanted the dimensions of the largest mailable parcel of that size. And so that would be X is 18. So in this case, it would be 18 by 18 by what would Y be? And that was right over here. Then you come back to this equation right here, right? So 108 minus, what's 4 times 18? 72. So 108 minus 72, 36. So 18, and what would that have been? Was that inches? So 2 marks, is that inches? 18 by 18 by 36 would be the size that would give us the largest ball. Okay? Now, somebody had asked about a cube. Okay? Now, this is part A. You could just do. I mean, part A. I mean, you don't even need the calculus part to do part A, right? Because in a cube, what would be the girth? The cube would be x by x by x, right? The girth would be 4x plus alongside x, which would be 5x. 5x equals 108, just what we did. It would be 21.6 by 21.6 by 21.6, right? What's that? Somebody try that. What's 21.6 cubed? So for part A, what's the largest Malable cube? As long as you did the girth equation like we just did and found it would be 21.6 by 21.6, what's that cube? Oh yeah, we did it twice. 10,077. That's the largest Malable cube. So somebody was asking earlier about why wouldn't you just do a cube? Because a cube is because you can get more volume, right? You can meet their requirements. An 18 by 18 by 36 inch package would hold more and still meet their requirements. Okay? All right, so cube is not the largest volume for your money in this case. Okay? All right, so 28C is going to be very similar to that. The difference in 28C is you're going to do cylinders. So here would be where the height is the long side, and then your other case would be where the, I guess, the diameter. Something like that, where this is the long side. Okay? So those would be your two situations there. Okay? And you're supposed to maximize volume. Now I'll help you with this. What's the volume of a cylinder? Pi r squared h. Area of the base, area of the bottom here, times the height. So that's your volume, but your two girth equations will be different, right? One will be perpendicular to this side, one will be perpendicular to this long side here. Okay? And so you guys can start working on that for the rest of the time. That might be a good thing to do. I will get the business packet to you here. And so you got 4.3 day 2, so there's 4 problems, 19, 21, 27. Now 19, let me see here. You can ignore part B, or no, excuse me, you can ignore part A on 21. On 21, you can just do part B. On 19, there isn't any calculus or anything to do on 19. 19 just kind of sets you up to do number 21. So 19 is more about, here's an equation, they give you some numbers, you plug in, you answer a question, they even maybe have you graph it, graph the thing, okay? It's about trajectory of an object. So they're talking about a football, okay? So in 19, that's pretty easy one, but just here's a formula, they give you some numbers you plug in, you just graph it maybe, but it sets you up to do some stuff on 21, which you are going to maximize, okay? And then 27 is a big part of, 27 and 28 are a big part of what we're doing. And we already went through 28. And then the business packet has a couple of problems.
What about 3 and 8?
That's the business packet. That's the business packet.
Just those.
Just those 2 problems in the business packet. And I'll get those run off and get to you, everybody. Okay?
You said 21 do B.
Do part B, do not do part A on 21. Just do 21B. Okay? Any other questions? Yes, you may. Third block, any questions?
That's a snazzy.
No? Okay.
I
All right.
have a question to start.
Get to work.
I have a question.
Yes.
Why did you ever divide 108 by 5?
Yeah, that's